Okay, so 7.5 says roots and zeros. So at the top of your paper, it talks about the difference between polynomial functions, or factors and zeros and all that sort of thing. So for a polynomial function, f of x, c is what we call a zero of the function. Remember, zeros are the same things as like solutions. X minus c is a factor. So if I write it with x, that's what we did last time on your homework. You found the factors, right? And then c is a root of the polynomial function if we set it equal to 0. All right, so things that mean the same thing. Roots, zeros, solutions, all mean the same thing. When I put them with the x, if it's x equals, then those are roots, solutions, and zeros. If I put it with the x, then it's a factor. Does that make sense? Questions on that? Just to get vocabulary so we're all on the same page. Okay. Well, then we have the fundamental theorem of algebra. And the fundamental theorem of algebra says every polynomial equation with degree greater than 0. And we talked about degree is the highest exponent. It has at least one root in the set of complex numbers. Okay, let's talk about what complex numbers are. Complex numbers, remember, have a real part and an imaginary part. Remember, that could be something like 3 plus 7i. That's a complex number. But it could also just be like 3 with no I. So that's a complex number. He's actually a real number, right? Because he just has the real part to it. He could also just be an imaginary number if it was like 0 plus 7i. Does that make sense? So what that fundamental theorem of algebra says is that the number of roots equals the degree. The number of solutions equals the degree. Okay, well, let's test that out. It says solve each equation and state the number and type of roots. Okay, if I were going to solve this guy, not too bad, right? Just add the 10. So A would be 10. How many solutions does that guy have? 1, right? And he's a real number. So he's got 1 real root. Good morning.
How's your weekend?
So far, so good.
Thanks.
I haven't had any complaints yet, so you know. Yeah. Yeah, how was yours?
Crested View, it was beautiful.
Nice. Yeah. Was it busy?
No, not really.
Oh, that's good.
They need a lot more snow, though.
Yeah, that's what I've heard.
Yeah.
Sweet.
Busy?
Yeah, this is a packed house.
How many kids are online?
12, 13.
Oh.
Yeah. We got 1 empty desk if you want to learn about roots and zeros today.
I think I'm good here.
Okay, good. Okay, so if we look at B, we've got a square, right? How would we go about solving that? Think back to chapter 6 before break. What are some things that we've done to solve that guy? Shayna? We could factor it. Okay, let's see if he factors. We got a plus and a minus, so it'll be a plus and a minus. I need 2 numbers that multiply to 48. That then subtract to give me 2. Harry.
6 and 8.
Perfect. And I want a positive 2, so I want a positive 8. And then my zero product property says if it's equal to 0, then one or both of them are equal to 0, and then I can solve. So I have x plus 8 equals 0 and x minus 6 equals 0. So x is 8 or x is 6. Okay, so we got 2 roots there. And our degree was 2. Okay, so how many solutions do you think we'll get here? 3. We should have 3 solutions. Now, are they all going to be real numbers? Probably not. Should we try it? Okay. First thing, we should probably see if they have anything in common. What do they have in common? An A. Anything else? A 3. Okay, let's pull it out. Okay, so 3a is equal to 0, or a is 0, so we got one root there. He's real. And then a squared plus 6 equals 0, so a squared equals negative 6. So I'm going to take the square root. I took the square root, so I get a plus or a minus. I have a negative under a radical, so it's going to come out as an I. And then I have root 6. So I have positive I root 6, negative I root 6, and 0. So one of them's real, and 2 of them are imaginary. See that? So what the really cool thing about that fundamental theorem of algebra says, it just tells me that whatever the degree is, see this guy had a degree of 1, his biggest exponent was 1, I had one answer, one root, one solution, 1 0. This guy, his degree was 2, he had 2 roots, 2 solutions. This guy was a degree of 3, and I got 3 solutions. So, if we were going to solve this guy, what do you think? How many roots would he have? 4, because my degree is 4. Does that make sense? That's the biggest thing I want you to take away from that. Do you want to solve this one, or you want to keep going? Solve it. Okay. This guy right here is the difference of squares. Would you agree with that? Okay, so does anybody remember how to factor the difference of squares? Thomas.
It would be y squared minus 4 in y squared.
Perfect. Okay, that guy right there's the difference of squares again, right? So let's factor him again. So that guy would be y plus 2, y minus 2, but that guy doesn't factor because of the plus. My zero product property says I can put those guys all equal to 0. So y equals a negative 2. Y equals a positive 2. And then this guy I'm going to solve like that one. So I'm going to move the 4 over. So y squared equals a negative 4. Take the square root. Y equals, I took the square root, so I get a plus or a minus. I have a negative under my radical, so I get an I. And the square root of 4 is 2. So I got two real solutions, positive 2 and negative 2. And I also got two imaginary solutions, positive 2i and negative 2i. So I had 4 roots. My degree was 4. I had 4 roots. Questions on that? Well, wouldn't it be cool if we could tell what kind of roots they had? Wouldn't it be cool if I could look at this guy right here and say, okay, you've got a positive root, a negative root, and 2 imaginary roots. So I knew what to do when I'm solving it, right? Or like this guy, it'd be nice to say, hey, I've got 1 real root, and then 2 imaginaries. That'd be pretty sweet, right? That'd be really helpful, especially as we're solving. Well, this really cool dude back in the day, Rene Descartes. Let me see if I can find you a picture of him, because he is very cool looking. You'll say, oh yeah, he has got the most amazing hair ever. Oh yes, I found him. Look at that bad boy. From 1596 to 1650, he was a French mathematician. Like, check out that hair, right? And a philosopher. One of his best-known quotations comes from the Discourse on Method, I think, therefore I am. So that's that dude, right? Okay, so he came up with this rule of signs. So it's Descartes' rule of signs. And it says, if I have some polynomial function with real coefficients, meaning I don't have any i's as my coefficients. We're not dealing with any of that sort of jazz, okay? Arranged in decreasing powers of, or descending powers of the variable. So, remember what I told you? We start with the biggest exponent and we write them smaller. So this is descending. Then, the number of positive real zeros is the same as the same number of sign changes in the signs of the coefficients. Or less than this by an even number. Okay, let's go investigate that part of his rule. It says it's equal to the sign changes in the coefficients. Okay, so let's go down here and look at number 2. I just want to look at the signs of the coefficients. Alright, so this guy has a positive 1, and then a negative 1, and a positive 2, and a positive 4. Right? He says look at the signs of the coefficients and look for sign changes. Okay, well I go from a positive 1 to a negative 1. Is that a sign change? Yeah. Alright, I'm going to count that as a 1. And then I'm going to go from a negative 1 to a positive 2. Is that a sign change? Yep, sure is. And then I go from positive 2 to positive 4. Is that a sign change? No. So he's saying, in his rule, the number of positive real zeros, the number of positive answers, is the same as the number of sign changes in the coefficients. So he's saying we could have 2 positive answers. But then he adds that or. All right, so we're going to make a little table. I call this my plus minus I chart. Because those are our choices for our answers, right? We can have positive solutions, we can have negative solutions, or we can have imaginary solutions, like we saw up here. Okay, so he said it's the equal to the number of sign changes, and then he added an or. Or less than this by an even number. Okay, less than. What does less than mean? Add, subtract, multiply, or divide? Subtract. Less than this by an even number. What's our smallest even number, not 0? 2. So he says take 2 away from that, and we're talking about positive answers. So everything in our chart needs to be a positive number, okay? So we're going to subtract 2 until you get to a 1 or a 0 and stop. So 2 minus 2 is 0. So his rule says we can get 2 positive solutions or we can have no positive solutions. You're like, well, that's not really helpful. Thanks, dude with really awesome hair, right? Okay, let's see if the rest of our table helps us. Questions on that before I go any further? Okay. Then he said the number of negative real zeros of y equals p of x is the same as the same number of sign changes in the coefficients of the terms p of negative x, or less than that by an even number. Okay, p of negative x. Think about it as f of negative x. I'm going to plug in a negative x everywhere I see my x. Sorry, that's a negative in there. Got a little crazy. Okay, so let's see what happens when I plug negative x in. What's negative x to the third power? Negative x, negative x, negative x. Is he positive or negative? Negative, so that guy becomes negative x cubed. And then I have negative x squared. Positive x squared, right? But he's already a minus, so he's going to stay a minus x squared. And 2 times a negative x becomes negative 2x. And nothing changed with the 4. So look at what happened when we did it by a negative x. It started out as an x cubed, he became a negative x cubed. It started out as a negative x squared, he's still a negative x squared. It started out as a positive 2x, it became a negative 2x. Started out as a positive 4, he stayed a positive 4. Essentially what happened? Which one's changed? The odd exponents changed. So here's your quick and dirty rule. So to get f of negative x, all you do is flip the sign of the odd exponents. And then we're going to count sign changes again. Alright, here we go. I went from a negative 1x cubed to a negative x squared. Is that a sign change? I went from a negative x squared to a negative 2x. Is that a sign change? I went from a negative 2x to a positive 4. Is that a sign change? Yes. If you have a 1, you have to pull it through your table. All right. How many total roots does this equation have? How many solutions should this guy have? 3, because our degree is 3, right? So in the total column, that has to be the same as your degree. And going across the row, we have to add up to 3. So 2 plus 1 is 0. 0 plus 1, I have to add to 3. So what do I need down here? 2. 2 plus 1 is 3. 2 plus 1 plus 0 is 3. Okay. And then 0 plus 1 plus 2 is 3. That's the number of sign changes of my f of negative x. So that's these guys. There was one sign change right here. Okay, let me tell you what this means. Let me draw you a picture. This means, this chart right here means I either have a graph that crosses my x-axis twice in the positive, once in the negative, and no imaginaries. So my graph could look something like that, because he's a power of 3, right? 1 negative root, 2 positive roots. The other option is I have no positives, but I have imaginaries. So the other option would be the bottom row, and it would be something like that. 1 negative, 2 imaginary roots. I still have 3 roots, but I know for a fact, based upon this chart, that it crosses once in the negative part of my x-axis. Does that make sense? Making the table, I'm sure, is still muddy. But do you understand what the table is telling us? The table is telling us what kind of answers we could potentially get. We either cross it twice, that would be the green guy, in the positives and 1 negative root, or I have 1 negative root and 2 imaginary. So if I'm going to go start finding roots, I want to start looking because I know for a fact I have a negative root. Right? I want to start looking for that guy first because I know it has to be there. Tomorrow I will help you come up with a list of things that could potentially be answers. But today I want you to see that we know for a fact we've got 1 negative root. All right, should we try making a chart again? Notice, all of the numbers in your chart should be positive numbers. These are potential roots. You can't have a negative number of potential roots. You can have negative roots, but I can't have a potential for negative 3 roots. Okay? The other thing I want you to notice is that this column right here is always even. Remember when we were doing them before? Imaginary roots are always in conjugate pairs. So that I column, it has to be always even. Okay, let's try this guy again. Let's make another chart. Plus minus I totals. Okay, looking at my polynomial, r of x equals x to the 4th minus 6x cubed plus 12x squared plus 6x minus 13. Are they in decreasing order of powers of their exponent? What's my degree? 4. So I know in the total column it has to equal 4. Okay, let's count sign changes. So I'm going from positive 1 to negative 6. Is that a sign change? Yep, that's 1. Negative 6 to positive 12. Is that a sign change? Yep, that's 2. Positive 12 to positive 6. Is that a sign change? No. Positive 6 to negative 13. Yes. That means that this guy could have 3 potential positive roots. It could cross the x-axis 3 times in the positive part from 0 on. And then my rule says subtract 2 until you get a 1 or a 0. So 3 minus 2 is 1. Now, if it were a number bigger than 3, say it were like 5, say we had 5 sign changes, it would be 5, subtract 2 would be 3, subtract 3 would be 1, 2 would be 1. Does that make sense? So you can have multiple rows based upon what your sign changes are. You don't have to have just 2 rows. Okay, now let's do f of negative x, or r in this case. Flip the signs of the odd exponents. Okay, well, 4 is even, so I'm going to keep him as x to the 4th. 3 is odd. He was a negative 6x cubed, so I'm going to flip him. So now he's a positive 6x cubed. 2 is even, so he's going to stay 12x squared. 1 is odd, so I'm going to flip him. He was a positive 6x, now he's a negative 6x. And you can think about the constant as like x to the 0. He never flips. Always keep it. So we keep, flip, keep, flip, keep. And now we will count sign changes again. Positive 1 to positive 6. Is that a sign change? Positive 6 to positive 12. Is that a sign change? Positive 12 to negative 6. Is that a sign change? Yeah, there's one right there. Negative 6 to negative 13. Is that a sign change? No. So, I know I have one negative root. This guy needs something here, though. So if you end up with a 1, you have to carry it through. Does that make sense?
If both rows are 1s, do you still just carry it down?
Yeah. Yeah. Well, if we started out with this, then you probably only have 2 roots. Does that make sense? Yeah. Okay, now it has to add to 4 going across. 3 plus 1 is 4. Do I need any more? 1 plus 1 is 2. How many more do I need so e equals 4? 2. So this guy, we know for a fact, also has one negative root. He can have 3 positives. Let me show you a picture. Okay. Maybe we should put him in the calculator and see what he actually has. Now we'll do that in a second. We know for a fact he's got 1 negative, so he could have 3 positive and he's a power of 4. So he probably does something like that. That could be the first one. 1 negative, 1, 2, 3 positive. Harry.
So if you had multiple of those, you would just like start with whatever number, subtract 2,
Yeah.
and carry the 1 down and fill the rest.
Yes. And we can also have different numbers in here too. This one just worked out that they were both 1s. Does that make sense? So we could have ended up with like 3 sign changes here in the negatives, and then we would subtract 2 as well. Does that make sense? So the other one would look something like maybe this. I don't know, I'm making things up. So this guy would have 1 negative, 1 positive, 2 imaginary. As opposed to 1 negative, 1, 2, 3 positive. Does that make sense? Okay, questions on that chart? Okay, turn the page. Yeah, go ahead, Thomas.
Is there
Sorry.
a possibility, like the power of 4, that one of like the humps just touches the x-axis and this is below it, and
Yeah, so it could be a double root there. So yeah, I mean for this guy right here, it could be something, we would then call it a double root. So it could be something like that. Yes, that is, oops, sorry. That's a possibility as well. So we would call that guy a double root, like when we had a parabola. So we would still have 1 negative, 1, 2, 3 positives. Yeah, good question. Okay, should we actually try to solve one of these? Ready, set, turn the page. Okay, so number 4 says find all the zeros of x cubed minus x squared plus 2x plus 4. First of all, how many roots are we looking for? Or zeros, if you will. 3. Our degree is 3. Okay. Let's do our chart. Okay, so let's count sign changes here. Well, we know our total column has to have at least one row of 3, so we'll see how many more it needs. Positive 1 to negative 1. There's one sign change. Negative 1 to positive 2. There's the second sign change. Positive 2 to positive 4. So how many potential positive roots do I have? 2. What am I going to put below the 2? A 0. All right. Now I'm going to do my g of negative x. Flip the signs of your odd exponents. So I have x to the third, so he's going to become a negative x to the third. And then I have an x squared, so he's going to stay a negative x squared. Positive 2 to the x is going to become a negative 2 to the x. And the constant always stays. Count your sign changes there. How many sign changes do you have there? 1. So, 2 plus 1 is 3. I don't need any more. 0 plus 1 is 1. I need 2 more. So there's my chart. My chart tells me what? What do I know for a fact? I have one negative answer, right? How do you think we could figure out what that negative answer is? Right? Ray says, I've got my calculator. Could we look at the graph? Yeah, let's do that. Okay, so I'm going to go to y equals, and I'm going to plug this guy in. X to the third minus x squared plus 2x plus 4. Tomorrow we'll come up with a list of numbers that are potential ones. Okay? Okay, let's go with the graph. If you're not sure about your graph, go look at your table about what's your negative root. Bless you. Where'd it cross the x-axis? -1, right? And also, if we look at our graph, which one is it? Do I have 2 positives, 1 negative, and no imaginaries? Or do I have no positives, 1 negative, and 2 imaginaries? There's no positives, but there's 2 imaginaries. It doesn't cross my x-axis over here at all. So I know the other 2 solutions have to be imaginary. And I also know from my graph that it crosses at -1. Okay, now think about last Tuesday. It's a week ago, I know, I'm sorry. How did we depress the polynomial? How did I get this guy right here? Or this guy right here? I did synthetic division, right? And when I did synthetic division, if it was a root, what did I get in my remainder box? 0. So now we're going to go do our synthetic division and get a 0 in our remainder box. Because I want to depress that polynomial. If I can get him down to an x squared, then I know that I can complete the square. I can factor it. I can use the quadratic formula. Okay? So I got to get it down to an x squared. All right, here we go. I've got a 1 and a -1 and a +2 and a +4. Oh, sorry. Thank you. This guy is equal to 1, so that's the one I want to put in here. So I want to put a -1 in here, and I should end up with a 0 in my remainder box. You okay? All right. Bring the first one down. -1 times +1 is -1. Add down. -1 times a -2 is a +2. Add down. -1 times 4 is a -4. Add down. We did indeed get 0 in our remainder box, which we should have because we looked at our calculator and it worked, right? So now my depressed polynomial is 1x squared minus 2x plus 4 equals 0. Okay, think back to when we were solving them in chapter 6. Our options were to graph them. Well, we did that, and it didn't cross at any other nice pretty places, right? Then we could factor him, but he doesn't cross at nice pretty places. He also has imaginary roots. So what are your 2 options when you're looking for imaginary roots? Give up. No, don't say that. What could we do to find those other 2 roots? factor, we could factor if he factors. But he won't factor because we looked at our graph, remember, and he doesn't cross at nice pretty places. He also has imaginary roots. So what were our two options when we wanted to find imaginary roots? You're on the right track. Think back to chapter 6. What were our 4 methods for solving? We graphed them, and then we factored. We had 2 other ones. Yeah, the quadratic formula, right? That was one. That's one option. Does that help? Complete the square. Since we know that they're imaginary, we have to use one of those 2 methods. Looking at this guy with a b that's even, I'd probably complete the square. With a b that's odd, not gonna lie to you, I'd probably use a quadratic formula. Because if he's odd, we have to divide it by 2 and we get fractions. So do with what you're comfortable with. Okay? This guy, I'm gonna go ahead and complete the square. It's been a while, right? Yowza. Alright, so completing the square, we move the constant and add in the box. So I have x squared minus 2x plus my box is equal to a negative 4 plus a box. I'm running out of room. Okay. My box is b divided by 2 and then square it. Well, here's my b divided by 2 and then square it. 2 divided by 2, square it. So put a 1 in your boxes. All right, remember, I'm forcing this guy to factor with the exact 2 same factors. X, keep the first sign you see as a minus. Remember, a minus and a plus will be a minus and a minus. Square root the box. Does that look familiar? So I have x minus 1 quantity squared is equal to a negative 3. Now what do I do? So I get rid of things that are squared. Square root them, okay? So I'm going to take the square root. I took the square root, so immediately I get a plus or a minus. What about that negative? Can I reduce the 3 in the radical? No, so I get I root 3. Last step, get the x by himself, so I'm going to add 1. So x equals positive 1 plus or minus I root 3. Okay, how many solutions do I have there? 2. I have 1 plus I root 3 and 1 minus I root 3. So, it said find all the zeros. How many zeros am I looking for? 3. Did I find 3?
Yes.
Yeah, I did. I got 2 here, and I got this guy from my graph, right? So what are my zeros? Negative 1 and 1 plus I root 3 and 1 minus I root 3. Look at that. How cool is that? I gave you an equation. Granted, we did it together, but that's okay. I gave you an equation. We knew it had 3 roots, and we found all 3 of them. I think this is the coolest. This is my favorite chapter. Everything has a solution. We know how many solutions it has. We can find all of them. Questions? Yeah, Jillian. The only thing is, Jillian, so when we did it in chapter 6, we only dealt with things that have an x squared. So now I'm going to give you things that have like an x cubed or an x to the 4th or an x to the 5th. I don't usually go beyond 5. So the powers are higher, the degrees are higher, so we're just finding more solutions. So you still have to use those things that we had before. So you still have to graph them or factor them and then complete the square. The power is just higher, or the degree is higher, if you will. Good question. Okay, anything else? Thomas.
Back on the last page, it said subtract 2 until you get a 0 or 1 and stop.
Yes.
So, just clarify, like if I had a 5 for the
Yeah.
positive, you would go to 1.
Right, so it would be if it had 5 sign changes, then you would go 5, 3, 1. Yes. So, I'm not ready to head there yet. We'll talk about your homework here in just a second, but then I'll help you. Okay? All right. The last thing. Today's kind of a beast. I'm sorry. The last thing is called the complex conjugate theorem, and we've dealt with the complex conjugate theorem before. Anytime that you find an answer that has an I in it, he becomes with a plus or a minus, right? We've had that before. So the complex conjugate theorem says that if a plus bi is a, oh, there's a word missing there, is a root of the polynomial function, then a minus bi is also a 0 or a root. So sometimes it will only tell you one of them. But based upon the complex conjugate theorem, we know the other one has to be as well. For example, skip that box for the second. For example, it says 5 says, write a polynomial function of least degree with integral coefficients whose zeros include 4i, 3, and negative 5. Well, if we have an I for an answer, then I need a plus and a minus. So based upon the fact that 4i is an answer, negative 4i also has to be a root. Okay? Now, I'm going to show you a quicker way to go backwards. So these are the ones where I'm giving you the answers and you're giving me the equation. This box right here is a faster way of doing that. Okay? Back in chapter 6, I believe it was, they didn't talk about the sum and the product of the roots. In fact, the whole book doesn't even talk about the sum and the product of the roots. But it makes our life easier. So the sum of the roots, we're going to add the roots together. And the product of the roots, you multiply the roots. And then you can write an equation as x squared minus that sum of roots times x plus the product of roots. So think about this as a faster way of adding complex roots together or making an equation with complex roots. Okay? All right, so let's think about what our roots are. Here it says number 5 says our roots are 4i. We know that now negative 4i is also a root. 3 and negative 5. You have to work with those imaginary roots together. Okay, so let's do that. X equals 4i, x equals negative 4i. The sum of those roots, if I add those two roots together, what do I get? 0. And if I multiply them together, negative 4i times 4i.
Negative 16i squared.
Negative 16i squared. And what do you know about I squared?
Just one.
Careful. Negative 1, right? So this guy becomes positive 16. So following this box here, that guy is x squared minus, my sum would be 0x, and my product would be plus 16, or x squared plus 16. That's the equation to get those two answers. Does that make sense? I've put it into this box here. So I put 0 here and positive 16 there. You have to work with the I ones together. So we have to now do it for the other two now, Jillian. Okay, so my other two roots then are 3 and negative 5. So I have to do the same thing. I have to add them together. What do you get? Negative 2. My product. Negative 15. So now I'm going to plug those two guys in as well. X squared minus, well, I have a negative 2, so it's going to be plus 2x minus, but it says plus, or plus a negative 15. And now we're going to FOIL that guy together or distribute him or do your multiplication or your lattice or whatever you like to do. I'm going to do a lattice. Do you have to do a lattice? No. X to the 4th. 2x cubed, 15x squared, 16x squared. Whoa, I missed the 15. Negative. There we go. 32x. 225, 235, 240. So my equation is x to the 4th plus 2x cubed plus 1x squared plus 32x, I ran out of room, minus 240. Probably should say equals 0. And you can't see it, I'm sorry. When we were doing them in the last chapter, remember we would just move it over, and so I would write that factor as x minus 3 and x plus 5. Remember all that? and then we'd FOIL it. You remember that? This is a faster way of doing that, because I'd still get x squared plus 5x minus 3x minus 15, so x squared plus 2x minus 15. That's the same as that. See that? Okay, are you ready for the last one? Notice too, sorry, I'm getting ahead of myself. We had 1, 2, 3, 4 roots. We got an x to the 4th. So do a double check to make sure you've got them all. Also notice, I don't have any i's in my answer. Okay, let's try the last one. I want to give you time to work. Number 6 says, write a polynomial function of least degree with integral coefficients whose zeros include -3 and 2 minus I. Is there another root that they didn't tell us? What's the other root they didn't tell us? 2 plus I. So my roots are -3, 2 minus I, and the one they didn't tell us is 2 plus I. So I have 3 roots. Remember, these guys, the real guys, don't have to come in conjugate pairs. So I have 3 roots. So when I'm all done, I should end up with an x to the 3rd power. These guys, I have to work with together. The ones with the i's you have to work with together. So let's do the sum and the product of those two. All right, so I have 2 minus I plus 2 plus I. What's my sum of my roots? 4. The i's are going to cancel. 2 plus 2 is 4. Product. Well, that would be 2 minus I times 2 plus I. It's a binomial, so I'm going to FOIL it. 4 plus 2I minus 2I minus I squared. If you remember their conjugates as well, remember when you multiply a conjugate together, those middle terms must drop out. I also know that I squared is -1. So this is -1 times -1, so it becomes a +1. So my product is 4 plus 1, or 5. So, here's my sum, here's my product. So I have x squared minus the sum would be 4 times x plus my product, which would be 5. So if I were to move these guys over and multiply them out, it gets really nasty. Because if I move them over, it'd be x minus 2 plus I, and then x minus 2 minus I. That looks pretty gnarly. You can go ahead and do it, but when you do it, you should end up with that guy. Does that make sense? How do I write that guy as a factor? Move him over with the x. So he would be x plus 3. He doesn't have anybody to do a sum and a product with because he's just by himself. Does that make sense? The sum and the product, you have to work with 2 of them at a time. Okay, now I'm going to multiply this guy out. Remember, you don't have to use a lattice. X cubed minus 4x squared plus 5x plus 3x squared minus 12x plus 15. Combining like terms, I get x cubed minus 1x squared minus 7x plus 15 equals 0. Double check. We had 3 roots. We got an x to the third. I don't have any i's as my coefficients, so we're good. Okay, I gave you a ton of stuff today. Today's a big day. There was a lot there in our theorems. Questions? Okay, that's all the notes. So let's turn the page and let's look at your homework. And I'm going to make it a wee bit easier for you. Let's do number 1 together. Or let's do 1 through 6 together. It says solve each equation. I don't need you to solve it. State the number and type. I don't care about the type. So let's just state the number of roots. The number of roots, remember, is equals the degree. So how about this guy? How many solutions is that guy going to have? 1. Hey, we got 1 done. How about this guy, number 2? 4 roots. Hey, we're making progress. Number 3, 5 roots. Number 4, 3 roots. Number 5, 3 roots. How about number 6?
4 roots.
4 roots. Hey, look at that. We already did 6. Okay, that's all I want you to do for those ones. Can you look at the degree and tell me how many solutions it should have? All right, 7, 8, 9, and 10. This is just the plus, minus, I total chart. Okay, that's all you have to do. So your counting sign changes. You don't have to solve it. You don't have to do anything else. You just have to do the chart. 11, 12, 13, 14, 15, 16, those are where you're going to do all of it. So you're going to do the chart. Then you're going to look at your graph, see where it crosses the x-axis. Then you're going to do the synthetic. And then you're either going to do complete the square or the quadratic formula. You will definitely need another piece of paper. And then 17, 18, 19, and 20. You're going backwards. I'm giving you the answers. Remember, they didn't give you all of them. So here, for number 17, they told you 3i. You need to realize that negative 3i is also a root. And like 18, they gave you 3 plus I. So 3 minus I is also a root. Okay, so those are the ones where you're going backwards. That's the one where it's x squared minus the sum times x plus the product. Okay?